Section 30.5, the quantum mechanical picture of the hydrogen atom. So we've seen at this point, Bohr's picture of the hydrogen atom, that it has these energy levels that depend on n. Well, quantum mechanics reveals that it's not just n, a single quantum number, that the energy levels, it's true that energy levels do have these discrete levels set by a quantum number. That's why we use the word quantum, just to say discrete. But it turns out that there's 4 different quantum numbers we need in order to determine the state of each hydrogen atom. So the first is the principal quantum number n. This is the same one that Bohr came up with. It determines the total energy of the atom, and it can only have integer values. So the lowest value n can have is 1, then it could have 2, it could have 3, and in general, the higher the n value, the larger amount of energy you have. So at this point, perfect agreement between Bohr and the quantum mechanical picture. But the other quantum numbers, the other discrete numbers that define the state of the hydrogen atom, the second one is the orbital quantum number, which is written with a script L. So this number determines the orbital angular momentum of the electron integer values. So L can have any value from 0 up to n minus 1. So if n is equal to 1, L can only be 0. But if n is equal to 2, L can then be 0 or 1, because it still is at n minus 1 values. And this orbital quantum number L can be used to calculate the angular momentum of the electron, where the angular momentum is noted with this capital L, and it's equal to the square root of the orbital quantum number times L plus 1 times Planck's constant h divided by 2 pi. So this one will tell us about how much angular momentum said electron can have. The third quantum number we have is the magnetic quantum number. So this one's known m sub L. The number determines the effect of a magnetic field on the energy of an atom. It was discovered by a scientist Zeeman, and he found that if you add a magnetic field, it can change the energy of the electron. And so this number tells us some about that. And it can go, the reason it's a subscript L is because its value is set by L, the orbital quantum number. So m sub L can go from negative L, following integer numbers, all the way through 0, all the way up to positive L. So it can take on a whole range of values. If L is equal to 0, m sub L is also equal to 0. But if L is now equal to just 1, then m sub L could be negative 1, 0, or positive 1. And m sub L tells us about the z component of the angular momentum. So within the overall angular momentum that we got in the last quantum number, we now can calculate the z component with the magnetic quantum number times h divided by 2 pi. Finally, last but not least, we have the spin quantum number, which is noted with an m sub s. This number is needed because the electron has this intrinsic quantity property called spin, sometimes referred to as spin up or spin down. And you could imagine it as the electron as it's orbiting the nucleus, that it's spinning, similar to the Earth orbiting the sun is spinning around or rotating. And so how it's spinning could be described by either plus 1/2 or minus 1/2. Regardless of all the other states, there's always 2 possible spin states. So that one is in many ways the simplest, but there are always those 2. So all of these rules are summed up in table 30.1, which shows the name of all 4 quantum numbers, the symbol that's used for them, and the allowed values, which is really handy as a reference. So with this in mind, let's look at an example of the Bohr model versus quantum mechanics. Determine the number of possible states for the hydrogen atom when the principal quantum number is A, n equals 1, and B, n equals 2. Well, for the Bohr model, the state is just set by the n value. So whether it's n equals 1 or n equals 2, the Bohr model says, great, you have a single state for each of those. Sweet. But quantum mechanics has a few more quantum numbers to consider. And so we can follow the rules for each of them as we're going through this. So we'll walk through first case A. So for A, we have n is equal to 1. That tells us, based upon the table, that L has to be at a max n minus 1. So the largest value L can have is 0. M sub L is plus or minus L. So M sub L is held to be 0. But then the spin quantum number can be plus 1/2 or minus 1/2. So that's where we break off in having two possible states. So given n equals 1, we now have two possible states, and we can write their quantum numbers as 1, 0, 0 plus 1/2 or 1, 0, 0 minus 1/2. So these would be our two states. Cool. So this is twice as much as the Bohr model, but it's only one more, right? Not that big of a deal? Maybe not. Well, what about when we go to n equals 2? What's that going to change? Well, it's going to first start with this L value, because L can go to up to n minus 1, but it can take on a few different values. So let's take a look at that. So with n equals 2, now L could have a value of 0 or a value of 1. The value of 0 is much the same as the previous example. When L is equal to 0, M sub L has to be 0, and then we could have two possible spin states. Cool. But once L is allowed to become 1, that opens up a whole range of values for M sub L, for the magnetic quantum number, right? It could be plus 1, 0, or minus 1. And each of these M sub L's can have two more states because of the spin number. So plus 1/2, minus 1/2. And so this brings up all 8 of these possible states where it's a different combination of quantum numbers of 2, 1, 1, plus 1/2, 2, 1, 1, minus 1/2, 2, 1, 0, plus 1/2, 2, 1, 0, minus 1/2, and so on and so forth as we go through. So this is now very different from the Bohr model. As your n increases, the quantum mechanical picture reveals that there is a pretty dramatic difference between the two models. So let's take a further look at this with a conceptual example of the Bohr model versus quantum mechanics. Consider two hydrogen atoms. There are no external magnetic fields present, and the electron in each atom has the same energy. According to the Bohr model and quantum mechanics, is it possible for the electrons in these atoms to have 0 orbital angular momentum, and B, to have different angular momenta? So I want you to think about this for a moment. So take some time to reflect on parts A and B and come up with an answer to each of them, and then we'll continue on. So please go ahead and hit pause now. Right, did you do that? Okay, well, let's think about the orbital angular momentum. Orbital angular momentum, in the Bohr model, we saw that orbital angular momentum was proportional to n. And n starts at values that are equal to 1. So it always has to be greater than 0. So the Bohr model says, no, we can't have 0 angular momentum. What about quantum mechanics, though? Quantum mechanics says that L is equal to the square root of L times L plus 1, along with this h over 2 pi. So what does this mean? Well, the scripted L, the orbital quantum number, can have values starting at 0. So greater than or equal to 0. So for quantum mechanics, the angular momentum can be 0. Could be something else too, but it's possible for it to be 0. So that's a solid start there. What about for part B, where we want to think about different angular momenta? Different angular momenta. Well, for the Bohr model, we know angular momenta is proportional to n. So if you have the same energy, and since there are no external magnetic fields that could change the energy levels, the only thing saying the energy is the n, so they must have the same n value. So no, they have to have the same angular momentum. But for quantum mechanics, we note that it's dependent on the L value, and there's a range of possible L values even within a given N value, assuming your N is 2 or greater. So it is possible in the quantum mechanic picture to have different angular momenta. So once again, going back to this table, you see that it depends on L for the angular momenta in the quantum mechanic picture, and L can take on different values that are limited by N, but again, as long as N is big enough, L can have different values and we can get different amounts of angular momenta, including 0. So we've seen that the quantum mechanical picture does have some key differences from the Bohr model. And it turns out it even differs in terms of the radius of where the electrons are. So this is the ground state of a hydrogen atom. N is equal to 1, L is equal to 0, m sub L is equal to 0. And the blue sheen here is actually a probability cloud of where the electron is located. So it's most likely to be located where the blue is thicker. It's a higher probability, but we don't know exactly where it is. The Bohr model says that it has to be at a set distance from the nucleus, from the center, given by the Bohr radius. And it turns out that radius is exactly the same as the most probable distance for the electron. So the Bohr model isn't wrong per se, it's just not complete. It's not giving us the full picture. It gives us a sense of the electron is most likely here, but there are other places the electron could be in this hydrogen atom. And this is only in the ground state. It turns out things get a little more complicated when you go up to N is equal to 2, to the first excited state, right? When N is equal to 2, L is equal to 0, m sub L is equal to 0, it looks somewhat similar, a little bit more complex probability distribution of where the electron is located. When you go to L is equal to 1, it looks very different, right? Where the electron is only on the top half or the bottom half, and it's nowhere in the middle here, which is pretty wild. So the quantum mechanical picture has confirmed some of the ideas of the Bohr model, but also enhanced the overall understanding of the atomic structure and where the electrons are located, how we can describe these different states. We'll continue with this in the next section.